Today I'm going to be talking about obviously the seismic reservoir characterization workflow, basically taking a high level look at what we're looking to achieve, our ambitions and our aims, illustrate that with some examples, and then have a look at the kind of what I would call the Ikon Science ethos or workflow that we would use, and obviously specifically how we would apply that in our RokDoc software. So we have two clear, rather basic at the high level ambitions at the beginning. We want to obviously refine or even define our understanding of reservoir architecture and the plumbing of the reservoir. So we need to know something about where the facies are and their relationships to each other. And we ultimately want to build more accurate property models of the subsurface. So extract as much information from seismic data and then update our geomodels and ultimately allow us to understand what's going on in the subsurface more clearly and basically apply quantitative interpretation techniques. So at a high level, fairly straightforward. And what I'm going to do, hopefully, is illustrate how we can achieve these ambitions and aims using a particular workflow and obviously how those tools are deployed within RokDoc. So we'll start off with some examples to illustrate the challenges or what we might get out of the workflow. So here we have a prediction made from seismic data. This is a two-way time thickness of hydrocarbon saturated sands. And obviously, quite quickly, we can start to say something about the distribution of those pay zones and the thickness, and therefore where we would like to drill the next infill well, or if it's a prospect where we're going to drill exactly. So, you know, quite obvious example of what we're looking to do with this workflow. If we go to this second example, it's a bit more detailed here. So in this case, we're actually looking at low porosity gas sands, where obviously fracturing is a key part of being able to produce those. And in this play, we've also got these coal bed seams, very thin subseismic resolution, and those are in the low acoustic impedance, those blue layers there. So this is one particular realization. So acoustic impedance estimated from seismic data, but clearly the details there are non-unique. So there are many different realizations which could equally well match the seismic data. And in this case, you can see we often do quite a good job at matching those three wells in terms of the coal beds. But of course, there'll be many other realizations which equally well match. Now, this particular section has been generated using our GIFI technology, which stands for Joint Impedance and Facies Inversion. And that actually allows us to get these higher resolution images, which of course is a benefit, a good thing. But equally, we also need to think about, are there many different scenarios and realizations we can generate in order to understand the geological uncertainty in this case? So actually, how sure can we be at a given pixel if there's a coal bed seam there or not? And as I say, in this case, it's important to identify those seams because it's crucial for our fracture planning. So geological uncertainty and being able to analyze that is, of course, key. And we'll have a look later at how we might do that. So if we think more about connectivity and the plumbing, this example is from a mature field in the North Sea that's undergone 38 years of production already. On that section map there, that slice through a facies prediction from seismic, we've got the positions of producers and injector wells indicated, the blue being, of course, the dark blue, the injector wells, and then the lighter green being the oil production, and the lighter blue being the water production. So this is for a particular timestamp vintage seismic data, and we can have a look and see actually if we start to predict between the wells the distribution of the hydrocarbon bearing sands, we can start to think about where is the bypass pay, how are the injectors performing. We can start to see on the lower left side here where we've got these darker blue injectors, we can start to see the halos and the waterfront. So we can start to make estimates of plumbing and connectivity. If we do this in a multi-vintage sense, we can almost do intra-well history matching. So beyond just having a look at production changes at the well locations, we can start to use the seismic data to try and validate our flow simulation model and update it. You know, as I said at the beginning, ultimately we want to be able to update our geomodels, geocellular models with information extracted from seismic data. And that's exactly what we see in this example here. So in the upper section, we have what might be traditionally called a traditional method of generating, in this case, net to gross property. We have a map on the left and a section on the right in the upper row, and that's based more or less on geostatistics using well data is a common way of doing it. What we as QI geoscientists would like to do is to try and update these things or use seismic information in them. So the lower section, or the map in the section in the lower row, are actually seismically derived net to gross. So in broad terms, we see a similar pattern in terms of the distribution of those channels, but we're getting a little bit more information, or actually a lot more information about distribution and connectivity when we start to extract information from the seismic data. And it's going to be a combination of these two. So you might have the interpolation being made with reference to some seismic attribute. If you can, there are questions about upscaling and resolution, of course, as well. But ultimately, as I say, we look to try and update those geocellular models based on the outputs of QI, or the QI workflow. And that's really ultimately what we're looking to achieve with this seismic reservoir characterization workflow. Now, again, looking at the workflow itself in stages, we base all of this on learnings that we derive at the offset well data. So it's all based on rock physics being, of course, the transform between the petrophysical properties that we're actually interested in and the seismic response that we observe between the well locations. So, of course, we need to understand the connection, derive our framework at the well locations first. And, of course, we need to make sure that the log data that goes into that framework is fit for purpose. So the first stage in any workflow that we do is something called log QAC, and the QAC stands for quality, availability, and consistency. So it's not just about where do we have issues with our well data, but it's about what are the strengths of the well data, where do we have particularly good coverage, but also consistency, i.e. do we see differences in elastic properties for different shale types, perhaps, different sands? Is there the impact of compaction, pore pressure, etc., and isotropy on the data? So it's a thorough review of not only the data quality, but also how do the responses change intra and inter-well. And of course, to do that properly, we need to have our petrophysical interpretation, which is essentially telling us what the rock types are and where the pay zones are. And these things, of course, warrant their own talk on, and we'll have following on webinar series on these. But some of the details, you need to have a petrophysical interpretation which is fit for rock physics, and that means things like interpretation in the overburden, calculating porosity from density, looking at the shear log data in detail as well. So there are some differences between maybe a more standard petrophysical interpretation and one that's used for rock physics. But once we have an understanding of where the issues might lie, and of course the interpretation, we need to do our conditioning, which you can do in a number of different ways, but the common way to do it is to derive basin-wide or regional trends for each lithology. So you have your VPVS and VP density trends that you then use to repair your logs, if you like. The first step in actually deriving the framework itself is the facies labeling. So we need to look at deriving a scheme which basically makes different labels for each elastically distinct rock type. So it's facies that the seismic will be sensitive to, if you like. Of course, there's an upscaling step involved as well. But once we have that schema in place, we then do the perturbations relative to those different facies. So we can, of course, start to look at the overlap or otherwise between each cluster. We can perturb properties, saturation, porosity, etc. in the reservoir, but it's all done relative to that facies labeling. And once we've got that, we can then look at things like, of course, your synthetic amplitude models that help us with seismic interpretation. We can also look at inversion feasibility, as in, again, what are the overlap or otherwise between clusters, and therefore, what is the geological uncertainty? if you're in the tertiary section, maybe there's less overlap between clusters. Therefore, there are only a certain number of combinations of facies which can give us the observed seismic reflectors. Or if you're in the deeper, maybe in the Jurassic section, there's a lot of overlap, and therefore there's lots of different combinations which could equally well explain the seismic response. So from a modeling phase, it's good to know that up front. But of course, when we get into the inversion in the next step, we want to be able to derive multiple realizations and assess the same uncertainty. But we need to do all this groundwork before we can go to the seismic data at all. So it's worth showing this now, just to make sure that you can't really do a robust QI workflow unless you've done the groundwork at the wells. It's all part of it. Once we do get to the seismic side of things, of course, again, we need to look at the quality, availability, and consistency of our seismic data. Is it fit for purpose for QI work? Is it being processed in an AVO-friendly manner? Are there multiples in the data? Are there any residual issues like residual move-out, etc.? And of course, we need to do a quantitative well-to-seismic tie, and that's part of the data quality assessment, of course. But we can't hope to do any predictive work unless we can actually tie the seismic at the wells to a reasonable level. Now, in RokDoc, of course, we have tools for assessing the quality of the seismic data. There are a number of attributes you can look at. We have different ways of doing that quantitative well tie, which, of course, also tells us the fundamentals about the phase and the amplitude content of the data, which we need to know to be able to interpret it. And we have tools for doing seismic data conditioning, or SDC. So that's things like residual move-out correction, filtering, etc. And of course, we need to review the impact of that by referring back to the well tie. So if the well tie, we don't want to be doing things which is harming the responses we're looking for, if you like, in the data. So we always need to, after each step of seismic data conditioning, is to actually make sure that we're improving the tie, because those conditioning steps can just as much remove our AVO anomalies as enhance them. But once we're there, we then progress into the inversion stage of things, so estimating impedances from amplitudes. And again, we go to our facies labeling. So we have that scheme in place from the wells, and now we need to estimate across the volume those labels. So typically you might use a Bayesian classification type approach, where you basically form a prior model based on the offset well data with upscaling, and then you classify each pixel in the volume into a label. And the reason we do that is, yes, number one, it gives us information about the architecture, but number two, we can't actually robustly predict the petrophysical properties we're actually interested in unless we know what rock type we're in. Because as rock physicists, we know that those trends and those models change per rock type. Therefore, if we're going to use those in a reverse sense, we need to know what rock type we're in. So we always need to get back to the facies, and it's not, it does have the benefit, of course, of giving us information about connectivity, etc. So the next step is, of course, to predict those petrophysical properties using our either more straightforward relationships or using rock physics model templates in a reverse manner. So you essentially have a calibrated model and you use that as a reverse lookup table. Our GIFI technology, which you may or may not be familiar with, but I mentioned very briefly earlier, basically directly inverts from amplitudes to facies and impedances. So you can then take that information and go on to predict your petrophysical properties. So you kind of bypass that necessity to perform the inversion and then do the facies labeling. And again, we'll have another webinar on GIFI at a later date. But ultimately, we need to then upscale into the geocellular models. We've briefly talked about uncertainty as well, but it's always worth keeping in mind. These kind of workflows aren't such that you can just come up with a final answer and say, that's the one we're going to use and move on. We need to at least think about or try and get some numbers on the uncertainty. So of course, the seismic data doesn't have all the information that we need to get to absolute rock properties. And if we're using an inversion technology, which requires us to provide a single low frequency model, we need to look at the impact on the model that you give it. If you've only got one, you have to maybe test different model types to see what's actually the impact on the final result. If we've got a narrow angle range, of course, we're going to have trouble or uncertainty at least with our AVO regressions. So you end up with a spread or uncertainty in the predicted VPVS. And of course, again, going back to what we were saying about the rock property overlap versus the noise, or given a certain amount of noise, if there's a lot of overlap, there's a lot more geological uncertainty because there are many different options or combinations of facies which can explain the seismic reflections that we observe. So we always need to be thinking about that rock property overlap. The first part of that, of course, as I say, is in the inversion feasibility. And then when we make assessments of the noise level in the seismic, we can then, that's the more thorough inversion feasibility. But we also need to try and estimate multiple realizations from the seismic and then assess those in terms of the spread of responses, the posterior probabilities, etc. Now, there's a whole load of other different sources of uncertainty, of course. Generally, the seismic quality, again, has it been processed in an AVO-friendly way? Is the relative offset scaling appropriate? Are there multiples in the data that we need to address if we can? Is anisotropy at play? And have we captured that in our framework? Are rock physics models all isotropic, or have we actually assessed the impact of anisotropy? And of course, there's always some kind of bias down to the exact software and the algorithms that are being used, and of course, the user's preference. So the second part of this talk is now focusing more on how we can do these things in RokDoc. So we'll have a quick look at some of the tools, and then we'll dive into the software for a quick 5-minute demonstration. And hopefully the idea is that you can see how you could quickly apply these types of workflows. So at a very high level, we have tools, of course, to perform inversion in RokDoc. We've got a number of different techniques. They're all run as recipes on the fly. So you parameterize a recipe and then you run it on whatever section or map that you wish. So for example, we have the techniques below. So petrophysical reflectivities is basically saying that the angle stacks are band limited estimates of reflectivity. Colored inversion, of course, has been around for a long time, and it's a fairly straightforward technique, but it does have its place. Certain times it's a preferred manner, in fact, because you have less assumptions to make. We have model-based inversion, either single stack or simultaneous, and we have our GIFI technology as well. This is an example of the Bayesian classification tool in RokDoc. So in this case, we have inverted impedances. We have some well data or impedances derived from the well logs. We upscale those, of course, to make sure that we're comparing apples with apples. And then we can use those to interactively fit a prior model. So the prior model for the Bayesian classification is a series of PDFs, so defined in elastic impedance space, but also with prior probabilities, which effectively is their relative heights to one another. So this tool will fit those to your clusters automatically. It gives you the prior probability given the working intervals and the wells that you've got. And then you can adjust those ellipses using those nodes that you see there. So interactively and on the fly, you can move those PDFs around, you can change the prior probabilities, and then without running any volumes, you can see the impact on the classification. And again, because this is set up in such a way that they're recipes, you can chain them together. So actually, you could do that whole workflow that we talked about from your angle stacks right through to your, say, porosity prediction from seismic, all as recipes without realizing anything. And that's great because, of course, it saves us volumes on disk, but it also means that if I went back to one of my seismic data conditioning steps and I changed the parameter, then the prediction of porosity at the end would automatically update. So it makes parameter testing very easy. The final step that we were looking at was using our calibrated rock physics templates in a reverse manner. So here we see a porosity prediction from seismic or from elastic impedances. And as I say, basically you have a calibrated rock physics model. You then make a lookup table and you basically feed in your inverted impedances, and the implied porosity or saturation is then given back to you from the lookup table. So what will follow next is a 5-minute demonstration of RokDoc in action. What we have here is a few windows. You can set these up as you wish. There's no limitation on how you do that. So here I've got 4 windows, 2 arbitrary lines on the left-hand side, and then a map viewer in the upper right and a 3D view. So what I'm showing at the moment is the simultaneous inversion window. We can apply that in PP or PP and PS mode. We can use a number of different reflectivity models in the forward model in the engine. And we can have a wavelet that varies not only vertically, but also laterally per angle. So we can capture variations in frequency and phase. We need to supply a low frequency model, which can come from any number of different places. And of course, there's a whole load of parameters in here, such as the relationship between the impedances that you're inverting for, the low frequencies that are retained within the model that you give it, and things like the model weight, as in how far can it wander from that starting model. We also have things such as the impedance factors, which control how tightly those trends are adhered to. We can make derivatives and QC outputs, of course, as we should. So things like looking at the relative quantities, so taking out the low frequency model. But when the inversion is run, it's only run on the line that you choose. Of course, we look at other QCs such as spectral plots, but this run as a recipe. So only in that top window has it been run, and we can show the AI on that section. We can show the synthetics and the residuals, etc., and any of those derivatives that we specified. So things like the low frequency model that you've used and how that looks. So that's all available as recipes. So you can really get into all of the different QC products that come with it. Of course, we need to run it at the well locations too. So that's a very easy process in RokDoc. We just choose the wells that we wish to show it at, and then you can make a multi-well viewer. You can look at cross plots and statistics, and really start to understand how well it's performing. Of course, you know, if you've got a low frequency model from the wells, the match will be generally quite good because it's got that low frequency. So here's an example. You can see the low frequency model in blue there, the inverted impedance in red, and the log impedance in black. And you can very quickly look at the matches in each of those wells you've chosen. You've got the synthetics and the residuals there as well, and the statistics. So it's all very interactive in how it's set up. And you can save these views to look at later. The cross plots show absolute impedances, log and seismically derived at the top and relative at the bottom. And again, it's another way of just comparing on a zone by zone basis, you know, how well it's doing. And of course, here we don't see such a great result for the density as expected for a PP inversion. So as I say, any of these things can be edited. So if I run it again, I can show on another line, the VPVS perhaps, if I run that same recipe, and I can actually then go in and edit any of the inputs to the inversion or the parameters as I wish. So for example, we might wish to apply some time alignment to the input, for example, and see what that looks like. But we also want to look at actually what does it mean in terms of the Bayesian classification. So again, now this is just run on that recipe. So it's another link in the chain where it's classifying the impedances into a discrete facies labeling. And then, as I say, I could go in and edit any of the inputs. So different recipes could go into there. Any of the parameters, the model weight, etc., can be edited, and we can have a look at it. And of course, another way, you know, you want to also map these things out. So this is just running a map, a horizon following slice through the Bayesian classification recipe. So it's running the inversion and the classification on the fly along that map. And then if I wanted to show it in 3D, I could also do that. So the RokDoc 3D viewer, you know, we've got some sections here, but you can also do 3D cubes and geobodies, etc. I'm just showing the facies logs at the well, so you can do that for all wells automatically. And, you know, maybe I'll go in here and edit the input to have maybe some time alignment applied, some residual move out correction. And if I then maybe look at the VPVS, because that's going to have the most obvious change if I do some alignment to the traces going in. So we can then look, that's after the alignment. If I then show a recipe where there's no alignment applied, you can directly see the impact on the VPVS of performing that alignment. So we can test the parameters very quickly. And indeed, if I change my alignment parameters in the previous recipe, I recalculate everything, and then on the fly, it updates. So all I've done there is gone back to my SDC, changed the alignment window length, and then I can go back in and say, actually, you know, how am I impacting my VPVS ratio in this case. And that applies for any recipes. So I rerun the Bayesian classification on the map, and now it's taking the output from the inversion, which has that alignment applied. So quite a small change in this case. But if I go in and take maybe some input seismic data, which has been filtered and aligned, so a more comprehensive seismic data conditioning workflow, I can then, of course, go in and have a look at the impact of that on my outputs. And that includes the porosity prediction here. So this is now in the lower left, a porosity prediction from seismic from those impedances, all again as a recipe. And if I run the map in the top right again, it's now going to show me the facies classification with the conditioned angle stacks going into that workflow. So the last thing that would be good to do before we go back to the slides would be to look at extracting some logs at the wells. So in this view here, I've got at the well locations, my porosity prediction from the seismic in red, and it's overlaying against the log derived porosity in black. You've got your seismic angle stacks there for reference and the volume fractions too. But this basically allows me to actually understand how well my porosity prediction is working. And again, if I changed any parameters from the seismic data conditioning to the inversion to the facies classification, or the way that the model is predicting porosity, these logs will automatically update on the fly. So rather than spending ages crunching through volumes and having a look at the impact, I can on the fly change parameters and then have a look at the impact on my actual result, which of course is what we're really interested in. So that's a very short look at how the software performs these workflows. And there's a couple more slides then before we wrap up. So to kind of summarize, of course, there's a lot more functionality in RokDoc than we've got time to look at today. But essentially, the reservoir characterization module allows us to basically take the learnings from the forward modeling and the well-based data. We can do these things interactively in a workflow-driven approach that we've just seen, come up with our different lithology and fluid distributions. A number of different inversions allow us to predict absolute properties. We can make many different low-frequency models, for example, and have a look at the impact of those, and ultimately use rock physics to predict petrophysical properties from seismic data. We can take in offset or angle stacks, gathers, and stacks into this. We can look at velocities, of course. We derive or define a framework in time or depth based on horizons. And as I say, we've then got multiple tools for doing seismic data conditioning. So things like structurally oriented filtering, frequency slice filtering, which targets the low frequencies. We've got a first order Taylor series expansion method to estimate time shifts between traces. So for residual move out is an obvious application there for small shifts, but it also allows us to back out time shifts from 4D data if that's the workflow that's being followed. And we've got a multi-geological scenario modeling workflow. So we can, for example, as I say, generate multiple low frequency models for a model-based inversion, and then run those all through the interactive inversion and have a look at the impact of those models on the result. And then we have tools at the end of it to look at, depending on the workflow that we followed, to look at the mean and standard deviation of the properties, to look at uncertainties, etc. So one thing, as I say, we might like to focus on in terms of uncertainty is the models that's used in a model-based inversion, the more conventional approach. So here we've got an example where you start on the left with your input seismic data, and there's any number of low-frequency models can be generated. So either directly interpolating all well data, maybe selectively taking out some of the highly deviated wells, for example. Maybe they've got anisotropy impacts on the velocity logs. We could even derive some based on trends and more horizon control. We then feed all of those through the inversion. So we make any number of low frequency models. And then ultimately on the right there, we've got basically from the inversion to a porosity prediction. We can then look at all of those porosity predictions and come up with a mean porosity in the upper right and the standard deviation in the lower right. So basically, without generating multiple volumes, I can do all of this as a recipe and come up with a final review of actually, in terms of just the low frequency model I'm using, what is the impact on my porosity prediction? So you can start to see, actually dig right down to say, if I choose a slightly different model, does it have a massive impact on my porosity prediction? If we go for a more deeper dive into uncertainty, we can turn to something like our RokDoc GIFI technology. So that's basically a Bayesian approach which inverts for posterior distributions of facies and elastic impedances. So on the left-hand side here, we've just got 5 examples of a facies prediction, 5 realizations. So these match the seismic in a global sense to the same level. And if you kind of take a long look at them from a stand back a bit, they more or less look the same, but it's the details where we get differences. So once we derive these sets of multiple scenarios and realizations, again as recipes, you can then do a multi-realization analysis. So for example, in the middle there, we're looking at ranking. So you've got in those plots on the y-axis, the probability of exceedance, and the upper one is versus net to gross, and the lower one is gross rock volume. You can then start to pick out individual scenarios which represent that uncertainty space, or you can do things like look at P50s, etc. So on the right, then we can start to make probabilistic estimates of reservoir and hydrocarbon presence, connectivity, etc. And all of this you can do in RokDoc, and we see some 3D visualization of that from our 3D viewer. So to wrap up, we basically, of course, want to predict facies and petrophysical properties from seismic data. That's the obvious goal as we set out at the beginning, but we also want to explore the uncertainty in those predictions. And RokDoc's the ideal place to do that. We've basically got a system which is backed up by not only a fundamental basis in rock physics, so using all the well-based tools that we have also in RokDoc, but bringing those forward into the inversions and into the seismic reservoir characterization tools, and ultimately using GIFI, you directly take those rock property trends into that, but doing it in such a way that it's actually achievable within pragmatic timeframes. So yes, we want to do a lot of high science and use the rock physics in there, but we need to deploy it in such a way that it's recipe based. We can test parameters very quickly. We can see the impact on the ultimate goal, so on the porosity or the saturation prediction. We can see that very quickly by using these chained recipes. Of course, there is additional functionality on that front. So we can use something like GIFI to directly invert for elastic properties. We can perform that inversion natively in depth, so invert depth seismic. And we have a connection to reservoir engineering. So we have the ability to, of course, load in flow simulation data directly into RokDoc for use in modeling workflows. So perhaps taking geological models and turning them to synthetic seismic, for example. But we can also upscale the outputs from the QI workflow back into the GeoGrid, into the geocellular model.
For more information on any of the functionality demonstrated here, please contact info@ikonscience.com or visit our website at www.ikonscience.com. Thanks for listening.